Previously we discussed this grid type of analysis or the grid analysis for straight bridges. So for curved bridges, these are some of the recommendation. Curved structure can be modeled either with curved elements or approximated with a series of straight elements between transverse lines. So you can see these are curved elements and straight lines are for the slab. When using straight elements to approximate curved beam, so you have to straight elements to approximate a curved beam. The maximum recommended central angle for the element is 3.5. So this element angle should be 3.5, not greater than 3.5. This angle. For skewed bridges, when the angle of skew is for skew type of bridges, so you know what skew bridges are. For example, this is one of the support and this is other of the support. So if the bridge is at some angle with the road or at some angle with the natural with the horizontal surface, then such type of bridges are known as skew bridges. So for skew bridges, when the angle of skew is less than 20 degrees, transverse line should be parallel to support. So for example, if the angle of skew is less than 20, you can see in this figure. So you can model the transverse lines as straight and the sorry, the longitudinal line and straight and the transverse at some angle. For skew greater than 20 degrees, the transverse run parallel to the support. So for example, if you have the greater than 20 degree, the transverse element will run parallel to the supports. So you see these are the supports and these are transverse elements. So the angle between them is 0. So these are running parallel to the supports. For small aspect ratio bridges, so you see for skew less than 20 and for skew greater than 20, this limit is same. So the transverse elements are perpendicular parallel to the supports. But if the aspect ratio is small, so what does aspect ratio mean? So aspect ratio is basically span length divided by span width. So this is a small aspect ratio. So for such type of skew bridges, if the skew angle is greater than 20, you can use the same modeling technique. Okay. For skew bridges which has an angle greater than 20, but the aspect ratio is small, so in that case, you have to. This is how you can model the skew bridge. So you the transverse element will be not be parallel to the support, but will be perpendicular to the longitudinal elements. So these are just basic guidelines. We don't use grid analysis mostly nowadays. What is the threshold value between large and small aspect ratio? There are no limits on this large and small aspect ratio, but you can. This is a thing about observation and experience. So you have to perform multiple analysis. So I told you that we do not perform such type of grid analysis uh, anymore. But this is a thing related to experience. So there are no threshold values given in codes or in literature about such type of aspect ratios. But if you see that, let's say that you see that in this span, it has a almost uh, same length and same width. But if you see in this, the length is almost 5 to 6 times greater than uh, the the width. So if you have a length greater than 2 or 3 times, then you can use this type of analogy. But for one or between 1 and 2, you can use this type of uh, designing technique. I haven't done such type of modeling, grillage modeling, because mostly we use CSi Bridge for our design and it takes into account all these factors automatically. Okay, so the shortcomings, one of the main shortcome of this is you cannot design warping torsion. So if any one of you know what is warping torsion, I it the main thing is that it cannot take into account the shear deformation. So warping torsion come into this. So anyone know what is warping torsion? Yes and no, you can respond with no as well, so it's not a problem. Okay, so I will presume that nobody knows. So we have two type of torsions. So one is, for example, no. Okay. So we have two type of torsion. One is I the common type of torsion in which torque is applied to a section and shear deformation occurs. So in this, the in-plane shear deformation occur if you view it from the side when cross section warps. So I cannot answer in this because torsion, warping torsion is an advanced mechanics of material topic, and I am just explaining to you that what are the limits, what is warping torsion and what is not. So this is a very complex topic and I cannot explain it. Is this for this you have also to study the cyclic integral and other stuff as well. So it is not a, I cannot explain it is in this topic. I can share material with you or a lecture with you where you can study yourself, but explaining this warping torsion in this class will not be feasible for me. So basically I was discussing about warping torsion. So this is a, for example, a box section. So if torsion occurs, so I am just wasting my time on drawing this. Let's see it on Google so you can. I mean, torsion happens when section warps. No, it does not happen. So warping torsion has some another criteria as well. Google. Okay. So in the common type of torsion, yes, this is a very good example of warping torsion. So you see, this is a typically how warping torsion. So in a common type of torsion that we study, so there are no deformation in this direction. The longitudinal direction, no deformation occur. But in warping torsion, this deformation occurs. So who is asking? Twisting is accompanied by bending in warping torsion, usually related to shear center. Okay. So the common type of torsion that we discuss in RC structure, so that is typically twisting about this axis, but no deformation occur in this direction. No deformation. For example, if this I beam was twisted in the common type of torque, so it will have no deformation. These deformation do not occur in the common type of torsion. Warping torsion is accompanied by basically deformation in the longitudinal direction as well. So this is the crux of warping torsion. So hope you got it, that in warping torsion we have this rotation as well, this deformation in the longitudinal direction as well. In the typical type of torsion we don't have this deformation. And torsion is not a very straightforward topic. It is a very complex topic, and so if there is any example, so hope you got what warping torsion and the common type of difference between the common type of torsion is. So this, you can see this image. In this image, this is a, if it is subjected to common type of torsion, only such type of shear flow will occur. But if it's subjected to warping torsion, then this type of deformation will also occur in the twisted element. So this is known as warping torsion. So it is not a concern in concrete element. It is basically a concern in steel structures mostly in the plate type of girders. So we do not usually are concerned if you are modeling common type of steel or concrete structures. Okay, so the next type of analysis is this plate with eccentric beam. So plate with eccentric beam, I had explained previously, and in CSI Bridge, this plate in eccentric beam type of analogy is used in this area object model. So let's say I model I update is as a shell type of element, and let me turn off the extrude option. So it will take some time. So in this type of analysis, the slab and the girders are separately modeled as shell type of. Sorry for the disturbance. I have to turn the software off. So this hope you got this, that in this type of modeling, what we do, that the slab is modeled as a shell element and the beams are also modeled as shell elements. So these are some of the recommendations and shortcomings. So now coming toward the software, we will model some of the superstructure elements in the CSI Bridge, different type of superstructure. I will model an I section and a box section. You will model the T section. This will be your home assignment. So you will model the T section and this box section. Sorry, this box section. You will no, sorry, this not. You will model this box section, and T section. I will model the I section and the other box section. So before as until the software opens, if someone has any answer questions, so they can ask. If someone has any question in what we have studied so far, they can ask. So the software is taking a bit time, so we can discuss it. Mr. Arvind, do you have any questions so far?
For these types of cross section, I was trying to do but I did one of these girders over the weekend. But I know that the software has, like for example, SAP has these software, you can import them already.
Yes.
And can import the sections in the software. So is there a place where we can import the sections into the software? For example, I wanted to do a Ashta girder, type 3 Ashta girder.
Type 3
Yeah, I couldn't import it. I don't know how to import it. Like for example, in SAP you can, because they have a library where these things are located and you can bring them in.
So in CSI also I suppose we have the type 3 type of girder. We have to, if it is available in SAP, then it will also be in the CSI. So let's check if it is present here or not. I haven't used. Let me check first what type 3 Type 3 is a box or an I?
It's an I.
Okay, type 3. So if type 3 is an I girder, then you can model it very easily in CSI. So it's not difficult modeling type 3I. So this is a type 3I.
Yes, yes.
So
I said not the model is to import. I was trying to see if I could import it.
so
was
why
already
do you
there.
want to import it if it is available already if you can model it easily in the CSI? So there is no need to import it. You can draw it very easily. You can go to frame section, uh, concrete, and here precast I. So you can give these values and it will automatically draw it for you. So there is no need to import such a type of section that you can draw very easily, because importing is sometimes does not work. It is a very tedious thing. If you have made any error in units, then you cannot it will does not give you accurate result, and it will export something else, a very awkward type of shape. So if you can draw a section, for example box or eye, you can draw them here. There is no need to import. So I will be drawing this eye section. So you can see how can we do that. So for example, I want to draw the so okay, so last time I told you that we can also export if for today I also discussed, and last time I also told you that if you want to, if you don't have any option, any specific type of or any default type of section, you can import it through this from DXF file. You can draw it in CAD and you can watch the previous lecture. The same procedure that we apply for the section designer, that we can use here as well. So no need to do that exercise again. So these are some of the default sections that are available in CSI. So for box girder, these are the default sections. For monolithic section, T-beam, solid girder, flat slab, these are default section. And for precast I, these are the default sections. So today I will be modeling this section and one of this section. The T and the box you have to do yourself. I will show you how you can draw this box, and then you have to assign the section as well. So for precast I, what you can do, first you will select the template of precast I. So after you select the template, this window will open. So journal data is, let's say I call it I deck. So slab material property. So we are using a 4000 slab material property. If you have any other material property, you can define it. All the predefined material will pop up here, and you can select any one. So I am modeling this bridge. So it has 4 I girders, and this is the dimension. These are the dimension of I girders. So number of interior girders. So number of interior girders to refer to these two girders. So you one thing more, in this template, you can see that anything that is mentioned here with T, for example, T2, T1, T2, uh, all these are present here. So you can look up to the symbol and place the value accordingly. For example, here you are asked number of interior girders. So these are the interior girders and these are the exterior girders. So in my in the section which I am modeling has two interior girders. So I will select two total width. So let's change the unit to, what are the units here? So these are in millimeters. So I will change the unit to millimeters. So the width is 10500. 10500. Girder longitudinal layout. So it is along the layout line. So these are placed along the layout line. So straight line. So for example, if you have a curved type of bridge and you select straight line, so the bridge will not be, the girders will not be placed curved along the layout line, but they will be placed straight. Okay, girder spacing constant. So yes, we have a constant spacing. So if you select no, so if you select no, then you have to specify these S1, S2, S3. These are the S1, S2, S3. If you have variable spacing, then you can specify them using this manual spacing. So I'm using yes. Constant girder frame section. So for example, if you have a different girder here, the girder section are different for each of the girders, then you can select this as no, and you have to assign the different sections, define them separately and then assign them here. So I am using, mostly we are using same sections in a single span or in a single section. So top slab thickness. So top slab thickness is top slab thickness not mentioned here, but let's say mostly we use 225. So let's say it is 225 millimeter. This is concrete haunch thickness. So these are the haunches. So this is known as haunch. These are provided to accommodate punching shear in the slabs. So typically in bridge slab, punching shear is not a issue of concern. So we do not provide haunches. But if you have a very slender or a very thin slab, then you have to provide them to resist punching shear. So in our structure, there are no haunches. So you see this window. What you if you perform any type of modification here, it will automatically change it to here, adjust it here. So I give the haunch is 0. So you see the haunches disappear here. A girder section. So there are this is the girder section. So I haven't defined, I have defined it previously, but I will define it again for you guys so that you know, especially Mr. Irving, so you know that how can we model an I type of beam in CSI. So you can model it from the material, from this material library as well, and you can also come here, frame sections. So you can define it, add new, recast I. So let me now define this section. So you see that these are the different dimensions that are mentioned. These are the different dimensions that are represented by that are represented for this figure. So for example, if you want to change the top thickness, so you see B1. So in my girder, the B1 is 700 millimeters. So I will click 700 millimeter, and let me zoom in here. So 700 millimeter. The next thing is this. This is referred here as D2. Okay, so D2 is here. What's the problem? Sorry, I wrote 7,000. So the next thing is D2. So D2 is 230. The overall depth is D1. So D1 is the overall depth is 940 to 210, 290, 130, and 230. Let me add them. 940 plus 410 plus 290 plus 130 plus 430. So 1800 is the total depth of the girder. So 1800 Thanks. Now, the next thing is D3. Either you can define it as we don't have any D3, we have this D4. So, okay. So you can either define this by D3 or D4. So I will define it by D3. So it is 130. Okay, D5 is the thickness of the bottom. So 290. Width of the bottom is B2, so it is 600. This is either D6 or D7. You can define it by both. So the D6 is 210. Okay, B3, so no B3 here. And B4 is the thickness of the web. So the thickness of the web is 190. And these are T1 and C1. These are not used in our structure, so we don't use them here. One thing more, this type of okay, there is a problem. So what I did, I put some values. Now it's okay. So this is how you can model an eye girder. So Mr. Arvind, you don't need to export it from AutoCAD. You can model it here. So I previously had drawn this I beam, and I will select that one. So you see it appears here. So the section you select is appeared. So it says, so here you have to look for this. If it is red and it's saying that the section is illegal, so as long as it has not turned legal, then you cannot, it will not, the CSI will give you error unless and until you sort out this error. So now moving toward the next option, fillet. So we don't have any fillet. So F1 is the dimension of this fillet, so it is 0. Similarly, we don't have this fillet number 2. We have a straight section, so it is 0. Okay, left overhang length. So overhang is basically from the center of the girder to the edge of the bridge. So from the center of the girder to the edge of the bridge, this is 1125. So 1125. L2 is also same. L2 is also to the right. So 1125. Okay, L3. Left overhang distance to fillet. So this is L3. So L3 is 0. We don't have any distance to the fillet because we don't have any fillet here. So this is also 0. What is T6? Right overhang thickness. So T6 is the thickness of this overhang. So it has the same thickness as the slab. So it will also be 225. So if it has some other thickness, then you have to, then you can specify it here. For example, if it has 300, so you see it will change here. So 225 is the thickness. So still the section is not legal. So okay, so you can check what is the, why it is giving you why section is not legal by clicking this sign, and the specified data is invert. The length L3 cannot be less than the half of the left or the exterior top girder width. Okay, so you have to provide this value either equal to this L3, or it should have accurate, or either this should be equal to the stop value, or it should have a separate value. But in our case, we don't have any fillet, so I will give it equal to 1125. Similarly here, 1125. So now section has turn legal. So this is how you can define a section in CSI. Loads, I will discuss in the 7th lecture how can you, these are the template for defining loads, so we will not discuss it here today. So this is how you can define a section in CSI. Okay, so this type of section is basically used as these sections are mostly covered in ASTO, and I girders are mostly pre-tensioned in the ASTO standards. In Pakistan, we uh, model them as post-tension, but in the American code, mostly I are pre-tension. So you see there is an option for tendon layout. So if you have a tendon layout data, you can edit the values here. So you see that in pre-tension we do not provide parabolic type of tendons. So mostly either we use hard tendon or straight one. So Mr. Arvind, this is for you, because we don't use these pretension here in Pakistan, but if you are doing it in your country, then you can also model tendon here and provide the specific data and the tendon properties here. So we are not using this because we don't model pretension. Uh, we do not model pretension here in Pakistan. We mostly do I in the form of post-tension girders. So this is how you can define an I girder section. So I will cancel this because I previously has defined this one. So this is the girder let. Now how you can assign this section to this bridge? So you will come to this bridge option, spans, spans, and double click on this. So you can select any one of these. So I select the I girder. So you can also select, for example, if you want to specify a T-beam bridge here and I girder bridge here, so you can select any of these. So if you have a bridge with a box girder section here and I girder section here, and mostly in the BRTs we use such type of configuration. So if you have different spans in different superstructure in different spans, then you can define them by you selecting any one of this. So now I select I. Okay, I will I will also remove the parametric variations. So spans, no. Okay, someone meeting, and okay, meeting ends in 1 minute, so I will update it. So okay, so you see that these tendons are default are already present in this. So this is how I got to look. The meeting is ending. I am sharing another link. You can join that. We can start the meeting again. I am sharing another link with you.